In example 3, we're going to be using the comparison test. We want to determine whether the series 5 over 2n squared plus 4n plus 3, going from n is equal to 1 to infinity, converges or diverges. Now, for large n, the dominant term in the denominator is 2n squared. So we compare the given series with the series 5 over 2n squared. And let's observe what happens. So we have 5 over 2n squared plus 4n plus 3, which is less than 5 over 2n squared, because the left side has a bigger denominator. So in the notation of the comparison test, we know that the sum as n is equal to 1 to infinity of 5 over 2n squared, we can factor out the 5 over 2, and now we're going to find the summation of 1 over n squared. Well, we know it's convergent because it's constant times a p-series with p is equal to 2 is greater than 1. And therefore, we can say that this series is convergent by part A of the comparison test. Now, although the condition we have this series is less than or equal to b subscript n, or the other variation in the comparison test is given for all n, we need to verify only that it holds for n being greater than or equal to n, where this capital N is some fixed integer, because the convergence of a series is not affected by a finite number of terms. And this is illustrated in the next example.